Imagine you're a tourist trying to see as much as possible in Manhattan. What's the best route? This is known as the Manhattan tourist problem, and it turns out it can help us solve core challenges in bioinformatics like comparing DNA and protein sequences. To start, let's define our problem by imagining that we have a city such as Manhattan. We can represent Manhattan as a grid of intersecting streets with attractions scattered along the streets. Now, if I start in the top left corner at the intersection of 59th Street and 8th Avenue, and want to end up at the bottom right corner at the intersection of 42nd Street and 4th Avenue, how can I maximize the number of attractions I visit? We can only move down or to the right. That way, we're always progressing towards our destination and not going backwards. To simplify this, we'll treat attractions as weights on the edges of our grid. Every time we pass an edge, we add the value of its weight, that is the number of attractions next to it, to our total score. This turns our city into a weighted directed graph where each edge points either down or to the right. We can now redefine our problem. Our new problem is to make a path through a weighted grid and maximize the sum of the weights along the path. Let's start from the top left corner and see how we can make the best choices along the way to reach the bottom right corner with the highest score. In our first step, it doesn't matter if we go right or if we go down. Either way, we don't encounter anything. We can give both of these nodes a score of 0. Let's just take a look at what happens if we go down. Once again, if we go right or go down, it doesn't matter, since there aren't any edges. So we can fill in some more zeros. If we look at what happens when we go right, however, we finally run into an interesting choice. If we go to the right again, then we have an edge with weight 1, so we'll increment our score by 1. If we go down, we'll have an edge with weight 0, and we won't increment the value. If we follow the example path on screen, we end up taking a path with a score of 6. There are plenty of different paths we can take that will lead to paths with different scores. At each point in the grid, we want to have taken the path that would have given us the highest total score to get to that point. So for every node, we take a look at the two possible paths leading into it, one from above or the one from the left, and we take the one that would have given us the highest possible total. Let's use this approach to begin populating the grid. The top left corner will have a score of 0. Neither of the edges next to it have a non-zero weight, so the adjacent coordinates will also just be 0. Now, let's take a look at the point at the intersection of 57th Street and 7th Avenue. Since there are no weighted edges going into the point, and both the point above and to the left of it are 0, the point's score is still 0. The scores of the intersections of 55th Street and 8th Avenue, as well as 59th Street and 6th Avenue, are also 0 by similar logic. If we now try and fill in the point at the intersection of 57th Street and 6th Avenue, however, we finally see something interesting. Above it, we have a 0, and there's no weight along the edge. To its left is a point that's also a 0, but the edge between the points has a weight of 1. This means that it has an attraction along the edge. If we were to take the path from the node above to get to that point, we would still be at 0 and not having passed any attractions. However, if we were to take the path from the node to the left to get to this point, then we would add the weight to get a score of 1. Therefore, we would want to take the path from the left. At this point, the maximum score we could have is 1, where we would take the path where we would come from the left node. The score at any point equals the maximum of two values, the score from above plus the edge weight from above, and the score from the left plus the edge weight from the left. By applying this rule across the entire grid, we can build up the best possible path at every point. And in the end, the score in the bottom right corner tells us exactly what we want to know: the maximum number of attractions we can visit on our journey from start to finish. Now that we've broken down the problem, I challenge you all to write out the solution in code yourself. If you have any questions, feel free to leave a comment. I've linked the solution I wrote in the description. While the problem might just seem like little more than a fun puzzle, it actually mirrors the same logic we use in genome alignment, an algorithm used for applications including comparing DNA sequences and assembling sequence fragments of genomes. If a video on alignment sounds like something that you would be interested in, please subscribe. Also, if you liked the video, please leave a like, and if you disliked it, press the dislike button and leave a comment explaining what I could do better. Before I end this video, I want to thank Dr. Philip Campo and Dr. Josh Kangas for teaching the pre-college program in computational biology at Carnegie Mellon University and sparking my interest in bioinformatics. Also, massive thanks to Grant Sanderson from 3 Blue 1 Brown for his videos that inspired me to make my own. Thank you all for watching, and I hope you all have a great day.